SKLearn exceptions. Description: these are exceptions that can be raised by scikit-learn SKLearn during model training or prediction. They indicate problems that have occurred during the process. Understanding these exceptions is crucial for debugging and improving your machine learning models. Inputs. Data. This refers to the input data provided to the scikit-learn algorithms for training or prediction. It includes features and target variables. Model. The specific scikit-learn model being used, such as a decision tree, random forest, or support vector machine. Exception message. A clear description of the error encountered. Error code. In some cases, a numerical code that helps identify the specific issue. Steps. Model initialization. Create an instance of the chosen scikit-learn model. Data preparation. Ensure data is formatted correctly for the model's requirements. Model training. Fit the model to the training data. Model prediction. Use the trained model to make predictions on new data. Metrics. Accuracy. The proportion of correct predictions made by the model. Precision. The proportion of positive predictions that are actually correct. Recall. The proportion of actual positive cases that are correctly identified by the model. F1 score. The harmonic mean of precision and recall. Visualization plots. Confusion matrix. A visualization of the model's predictions, showing true positives, true negatives, false positives, and false negatives. ROC curve. A plot of the true positive rate TPR against the false positive rate FPR at various thresholds. Precision recall curve. A plot of precision against recall at various thresholds. Regularization parameter controls the complexity of the model to prevent overfitting. Learning rate determines the step size taken during optimization. Number of estimators. The number of individual models used in ensemble methods like random forests. Confidence intervals provide a range of values that the true prediction is likely to fall within. Bayesian inference uses probabilistic methods to estimate the uncertainty of model parameters. Challenge 1 value error expected 2D array. Got 1D array instead. Sample use case that resulted in challenge 1. A model like linear regression requires a 2D array for features, but a 1D array was provided. Fixes to challenge 1. Reshape the input data into a 2D array using the reshape method. Ensure that the data is properly loaded and has the correct dimensions. Challenge 2 value error input contains none, infinity, or a value too large for D-type float 64. Sample use case that resulted in challenge 2. The data contains missing values none or values that are too large to be represented by the data type. Fixes to challenge 2. Impute missing values using techniques like mean imputation, median imputation, or KNN imputation. Scale or transform the data to avoid values that are too large. Challenge 3 value error found input variables with inconsistent numbers of samples. Sample use case that resulted in challenge 3. The training data and test data have different numbers of samples. Fixes to challenge 3. Ensure that both the training data and test data have the same number of samples. If necessary, split the data into train and test sets with an equal number of samples. Challenge 4 value error unknown label type continuous. Sample use case that resulted in challenge 4. The model is attempting to predict a continuous target variable, but the model expects a categorical variable. Fixes to challenge 4. Check the data types of the target variable and make sure they match the model's requirements. If necessary, convert the target variable to a categorical type. Challenge 5 value error input contains infinity or a value too large for D-type float 64. Sample use case that resulted in challenge 5 data contains very large or infinite values, which cause overflow issues for the float 64 data type. Fixes to challenge 5. Scale the data to a smaller range, using methods like standardization or normalization. Use alternative data types like float 128 if necessary, to accommodate larger numbers. Challenge 6 type error. None type object is not callable. Sample use case that resulted in challenge 6. A function or method is being called that has not been defined or assigned correctly. Fixes to challenge 6. Ensure that the function or method is properly defined and assigned to a variable. Check the function's parameters and arguments to ensure they are passed correctly. Challenge 7 type error not supported between instances of str and int. Sample use case that resulted in challenge 7 comparing a string with an integer using a comparison operator that expects numerical data. Fixes to challenge 7. Ensure data types match when performing comparisons. Convert the string to an integer using the int function. Challenge 8 attribute error. List object has no attribute fit. Sample use case that resulted in challenge 8 attempting to call the .fit method on a list object, which doesn't have that method. Fixes to challenge 8. Ensure the data being used is a valid data structure supported by SKLearn, such as a pandas data frame or a NumPy array. Double-check the variable names and ensure that the object is a SKLearn model instance. Challenge 9 index error. List index out of range. Sample use case that resulted in challenge 9 trying to access an element in a list that is beyond its boundaries. Fixes to challenge 9. Double-check the index being used to access the element. Ensure the index is within the bounds of the list. Challenge 10 key error. Sample use case that resulted in challenge 10 attempting to access a key that doesn't exist in a dictionary or a column that doesn't exist in a data frame. Fixes to challenge 10. Double-check the key or column name for accuracy. Ensure that the key or column is present in the data structure. SKLearn exceptions convergence warning. Description. The convergence warning in SKLearn indicates that an optimization algorithm used in a machine learning model has not fully converged to a satisfactory solution within the specified number of iterations. This means the algorithm might have stopped prematurely, potentially leading to suboptimal model performance. Inputs. Data. The input data used for training the model. Model. The specific machine learning model being used, such as linear regression, logistic regression, or support vector machine. Hyperparameters. Parameters controlling the behavior of the model and the optimization process, such as the learning rate for gradient descent or the number of iterations. Outputs. Model. A potentially partially trained model with parameters that may not be fully optimized. Warning message. A convergence warning message is issued by SKLearn to signal the potential issue. Steps. Model training. The model is trained using the specified algorithm, typically involving iterative optimization. Convergence check. During training, the algorithm monitors progress toward convergence. Warning trigger. If the algorithm does not converge within the set number of iterations or reaches a specific stopping criterion, a convergence warning is raised. Metrics. Loss function value measures how well the model fits the data, often decreasing with successful optimization. Gradient norm represents the magnitude of change in the model's parameters during optimization. Visualization plots. Loss function plot visualizes the loss value over iterations, revealing convergence patterns. Gradient norm plot shows how the gradient norm changes over iterations, indicating optimization progress. Fine-tune parameters. Max iterations. Increasing the number of iterations allows for more optimization attempts, potentially leading to convergence. Learning rate. Adjusting the learning rate can influence the speed and stability of optimization. Uncertainty methods. Bootstrap aggregation bagging, combining multiple models trained on different subsets of the data to estimate uncertainty. Bayesian optimization, using a probabilistic framework to search for optimal hyperparameters while considering uncertainty. Challenges and fixes. Challenge 1. Insufficient iterations. Sample use case. Training a model with a small number of iterations might not allow the algorithm to find a good solution. Fixes. Increase the number of iterations allowed for training. Challenge 2. Learning rate issues. Sample use case. A learning rate that is too large can lead to oscillations and prevent convergence. Fixes. Adjust the learning rate, potentially using techniques like adaptive learning rate methods. Challenge 3. Data complexity. Sample use case. Highly nonlinear data or complex relationships might require more iterations or different optimization algorithms for convergence. Fixes. Consider using more advanced optimization algorithms like stochastic gradient descent (SGD) with momentum or ADAM. Challenge 4. Local minima. Sample use case. The optimization process might get stuck in a local minimum, where further iterations do not lead to significant improvement. Fixes. Use techniques like random restarts or simulated annealing to escape local minima and explore the search space more effectively. SKLearn exceptions. Data conversion warning. Description. The data conversion warning is triggered when scikit-learn encounters data that needs to be converted to a different data type before it can be processed. This usually happens when you feed data with inconsistent types, e.g., a mix of strings and numbers, into a machine learning model. Inputs. Input 1. Data with inconsistent data types. For example, a pandas data frame with columns containing strings, integers, and floats. Input 2. A scikit-learn model or function that expects data of a specific type, e.g., a numeric matrix. Output 1. A warning message indicating that data conversion has occurred. Output 2. The converted data, which may be a different type than the original input data. Steps. Step 1. Scikit-learn checks the data type of the input data. Step 2. If the data type is incompatible with the model or function, scikit-learn attempts to convert the data to a compatible type. Metrics. Metric 1. Accuracy. How well the model performs after the data conversion. Metric 2. Performance. How efficiently the model processes the converted data. Visualization plots. Visualization plot 1. Scatter plot or histogram to visualize the distribution of data before and after conversion. Visualization plot 2. Feature importance plots to see how data conversion affects the importance of different features. Parameter 1. Data type conversion method. Specify how scikit-learn should convert the data, e.g., using ASType or tonumeric. Parameter 2. Handling of missing values. Determine how scikit-learn should handle missing values during conversion, e.g., replacing with a default value or removing the missing values. Uncertainty method 1. Confidence intervals. Estimate the uncertainty in the model's predictions based on the converted data. Uncertainty method 2. Bootstrap resampling. Create multiple datasets by resampling the converted data and observe the variability in model performance. Challenge 1. Data loss during conversion. Converting data to a different type might lead to loss of information. especially when converting from strings to numbers. Sample use case that resulted in challenge 1: converting categorical features e.g. small, medium, large to numerical values e.g. 1, 2, 3. Fixes to challenge 1: use one-hot encoding to convert categorical features into binary vectors. Challenge 2: unexpected data types. The input data might contain unexpected data types, leading to unexpected behavior during conversion. Sample use case that resulted in challenge 2: data with mixed data types e.g. a column containing numbers and strings. Fixes to challenge 2: pre-process the data to ensure consistent data types before feeding it to the model. This could involve converting strings to numbers or handling missing values appropriately. SKLearn exceptions. Data dimensionality warning. Description: this warning is raised by scikit-learn SKLearn when there's a potential mismatch between the dimensionality number of features of your data and the expectations of the machine learning model you are using. It's a friendly reminder that something might be off and your model's performance could be affected. Inputs: data: the dataset you are feeding into the model, often represented as a NumPy array or pandas data frame. It includes the features columns used to make predictions. Model: the specific machine learning algorithm you are employing, e.g. linear regression, decision tree, k-nearest neighbors. Each model has its own assumptions about the data's structure. Outputs: warning message: the data dimensionality warning itself, printed to your console. Model performance: the accuracy, precision, recall, or other relevant metrics of your model, which might be impacted by the dimensionality issue. Steps: data preparation: ensure your data is cleaned, pre-processed, e.g. scaling, encoding, and ready for the chosen model. Model selection: select a model appropriate for your data type and task. Model training: fit the model to your training data. Model evaluation: evaluate the trained model's performance on unseen data. Test data. Metrics: model accuracy: the percentage of correct predictions. Precision: the ratio of true positives to the sum of true positives and false positives. Recall: the ratio of true positives to the sum of true positives and false negatives. F1 score: a harmonic mean of precision and recall. Visualization plots: scatter plots visualize the relationship between features and the target variable to identify any potential outliers or patterns. Feature importance plots identify which features are most impactful for the model's predictions. Fine-tune parameters. Regularization parameters: adjust parameters in your model, e.g. L1, L2 regularization to control for overfitting and improve generalization. Feature selection techniques: apply methods like feature importance ranking or dimensionality reduction, e.g. PCA. ELDA to remove irrelevant or redundant features. Uncertainty methods. Confidence intervals estimate the range of potential outcomes for predictions, considering the model's uncertainty. Ensemble methods combine multiple models to average predictions and reduce variance, leading to more robust results. Challenges and fixes. Challenge 1: incorrect feature dimensionality. Sample use case: you are using a linear regression model, expecting 10 features, but your data only has 5 features. Fixes to challenge 1: feature engineering: create additional features by combining existing ones or applying domain knowledge. Data imputation: fill in missing feature values using appropriate techniques, e.g. mean, median, or model-based imputation. Challenge 2: redundant or irrelevant features. Sample use case: your data contains many highly correlated features, or some features have little predictive power. Fixes to challenge 2: Feature selection apply methods like recursive feature elimination (RFE) or feature importance ranking to identify and remove redundant or irrelevant features. Dimensionality reduction use techniques like principal component analysis (PCA) to reduce the number of features while retaining most of the variance in the data. Challenge 3 data transformation issues. Sample use case: your data is not scaled or normalized, and this disrupts the model's assumptions. Fixes to challenge 3. Data scaling: use methods like min-max scaler or standard scaler to bring features to a similar scale. Data normalization: apply techniques like Z-score normalization or quantile normalization to adjust the distribution of features. SKLearn exceptions efficiency warning. Description: explain in detail. No applicable inputs. No applicable outputs. No applicable steps. No applicable metrics. No applicable visualizations. No applicable parameters. No applicable methods. Potential for inefficiency in the algorithm's implementation. Example: a model with a large number of features might cause the algorithm to be computationally expensive. Use feature selection techniques like PCA. Feature importance to reduce the number of features. Consider using a more efficient algorithm for the task. Use of a less efficient algorithm or a poorly configured algorithm that might lead to longer training or prediction times. Example: a linear regression model might be inefficient for highly nonlinear datasets. Choose a more suitable algorithm for the dataset and tune its hyperparameters to improve efficiency. Potential for memory inefficiencies during the training or prediction process. Example: a large dataset with a high number of features can lead to memory issues. Consider using techniques like data chunking or batch processing to handle large datasets. Use more memory-efficient data structures and algorithms if possible. SKLearn exceptions fit-failed warning. Description: the fit-failed warning is a warning issued by SKLearn when a model fails to fit the training data properly. This often happens when the model encounters issues like perfect collinearity in features, a lack of convergence during optimization, or insufficient data inputs. Training data: this is the dataset used to train the machine learning model. It typically includes features independent variables and target labels dependent variables. Model: this refers to the specific machine learning algorithm chosen for the task. Examples include linear regression, decision trees, support vector machines, etc. Outputs: fit-failed warning: this warning is emitted by the SKLearn model's fit method. It informs the user that the model has encountered difficulties during the fitting process. Model object: even with a warning, the model object might be fitted, but its performance might be unreliable. Steps: the model is initialized with chosen parameters. The model's fit method is called attempting to learn patterns from the training data. If the model fails to converge, fit properly, or encounters issues, the fit-failed warning is triggered. Metrics: training score: this metric assesses the model's performance on the training data. It can be helpful to identify potential overfitting if the training score is significantly higher than the validation score. Validation score: this metric evaluates the model's performance on a separate dataset, typically called the validation set, which is not used for training. It helps gauge how well the model generalizes to unseen data. Visualization plots: residual plots: these plots show the difference between the actual target values and the model's predictions. They can reveal patterns in the model's errors and suggest potential issues. Feature importance plots. These plots highlight the relative importance of different features in the model's decision-making process. They can help identify features that are contributing most to the model's performance. Fine-tune parameters. Regularization parameters. These parameters help prevent overfitting by adding penalties to the model's complexity. Examples include L1, L2, and elastic net regularization. Learning rate. This parameter controls the step size during optimization. A smaller learning rate can lead to slower convergence but may improve stability. Number of iterations. This parameter specifies the maximum number of optimization steps allowed. Increasing the number of iterations might improve convergence but can also lead to longer training times. Uncertainty methods. Confidence intervals. These provide a range of values within which the true prediction is likely to fall, considering the model's uncertainty. Bayesian methods. These approaches incorporate prior knowledge and uncertainty into the model's learning process, resulting in more robust predictions. Challenges and fixes. Challenge 1. Perfect collinearity in features. Sample use case. A model being trained on data containing two features that are perfectly correlated, e.g., weight in kilograms and weight in pounds. Fixes. Feature selection. Remove one of the perfectly correlated features. Regularization techniques. Use L1 or L2 regularization to penalize large weights and encourage the model to rely on a smaller subset of features. Challenge 2. Lack of convergence during optimization. Sample use case. The model's optimization algorithm might fail to converge to a stable solution due to issues like a high learning rate or a poorly initialized model. Fixes. Reduce learning rate. Experiment with smaller learning rates to improve convergence stability. Increase number of iterations. Allow the optimization algorithm to run for more iterations to reach a more stable solution. Try different optimization algorithms. Experiment with different optimization methods, e.g., gradient descent, ADAM, SGD to see if one performs better. Challenge 3. Insufficient data. Sample use case. The model might struggle to learn meaningful patterns with a limited amount of training data, potentially resulting in overfitting or poor generalization. Fixes. Gather more data. The most straightforward solution is to obtain additional training samples. Use a simpler model. Choose a less complex model that requires fewer data points to learn effectively. Employ data augmentation techniques. Synthetically generate new training data by transforming existing samples. SKLearn exceptions. Inconsistent version warning. Description. The inconsistent version warning in SKLearn is a warning that indicates a potential issue related to the version of SKLearn being used in the versions of other libraries that SKLearn depends on. It warns that the combination of versions might not be fully tested and may lead to unexpected behavior or errors. Version of SKLearn. The version of SKLearn currently being used. Versions of dependent libraries. The versions of other libraries that SKLearn relies on, such as NumPy, SciPy, and Pandas. Warning message. A warning message displayed in the console, indicating the inconsistency in library versions. Potential errors. The potential for unexpected behavior or errors in the SKLearn model due to the version mismatch. Check library versions. The code automatically checks the versions of SKLearn and its dependent libraries. Version comparison. The code compares the versions of these libraries against known compatible versions. Issue warning. If an inconsistency is found, the code triggers the inconsistent version warning to alert the user. None. The warning doesn't directly measure performance or accuracy. It's a signal for potential issues. None. The warning doesn't directly measure performance or accuracy. It's a signal for potential issues. None. This warning doesn't involve any visualizations. None. This warning doesn't involve any visualizations. None. This warning is not related to parameter tuning. None. This warning is not related to parameter tuning. None. This warning doesn't involve any uncertainty quantification methods. None. This warning doesn't involve any uncertainty quantification methods. Challenge 1. Unexpected behavior or errors. Using a specific combination of versions might lead to unexpected results or errors in model training or prediction. Updating the versions of SKLearn and its dependencies to the latest compatible versions can often resolve such issues. Challenge 2. Incompatibility with other libraries. Using an older version of SKLearn might not be fully compatible with newer versions of other libraries, causing conflicts and errors. Updating all the libraries involved, including SKLearn, to the latest compatible versions can help avoid conflicts and maintain consistency. SKLearn exceptions. Not fitted error. Description. The not fitted error exception is raised when you attempt to use a SKLearn estimator such as a classifier, regressor, or transformer before it has been fitted to the training data. In simpler terms, you are trying to make predictions or apply transformations using an estimator that hasn't learned any patterns from the data yet. Inputs. Training data. This is the data used to train the estimator. It typically contains both input features and corresponding target values for supervised learning. Estimator. The SKLearn model you want to train, such as logistic regression, decision tree classifier, or standard scalar. Outputs. Fitted estimator. After training, the estimator learns the underlying patterns from the data and becomes ready for making predictions or transformations. Predictions or transformations. Once fitted, you can use the estimator to make predictions on unseen data or apply transformations to existing data. Steps. Training. Fitting. This is the process of feeding the training data to the estimator to learn patterns, prediction or transformation. After training, you can use the fitted estimator to make predictions on new data or apply transformations to existing data. Metrics. Accuracy classification. A measure of the model's ability to correctly predict class labels. Mean squared error regression. A measure of the average squared difference between the model's predictions and the actual target values. Visualization plots. Decision boundary classification. A visualization that shows the regions in feature space where the model predicts different classes. Residual plots. Regression plots that show the difference between the model's predictions and actual target values. Fine-tune parameters. Regularization parameters controls the complexity of the model to prevent overfitting, e.g. see in logistic regression. Tree depth or splitting criteria. Decision trees determines the complexity and depth of the tree, impacting the model's ability to fit complex patterns. Uncertainty methods. Confidence intervals. Regression quantify the uncertainty associated with the model's predictions. Probability estimates. Classification provide probabilities for each class label, indicating the model's confidence in its predictions. Challenges and fixes. Challenge 1. Attempting to predict or transform before fitting. Sample use case. Trying to use model predict XTest without first calling model fit xtrain. Y train. Fixes. Make sure to call model fit xtrain. Y train before attempting to use the model for prediction or transformation. Challenge 2. Forgetting to fit a model after modifying its parameters. Sample use case: changing the regularization parameter in logistic regression but forgetting to refit the model. Fixes: ensure that you refit the model after any parameter changes using model fit xtrain. Y train to retrain the model with the new parameters. SKLearn exceptions: undefined metric warning. Description: this warning is issued by scikit-learn SKLearn when a metric is calculated for a dataset where the metric is undefined or not meaningful. This typically happens in situations where the target labels have only one unique value. For example, if all samples in your dataset belong to the same class, calculating metrics like accuracy or F1 score becomes meaningless. The predicted values are all the same if your model consistently predicts the same class for all samples, regardless of the true labels. Metrics like precision, recall, and F1 score will not be informative. Inputs: data: the dataset used for training and evaluation, consisting of features and target labels. Model: the machine learning model used to make predictions. Outputs: predictions: the model's predicted class labels for the dataset. Metrics: the calculated performance metrics, which might be undefined or not a number due to the warning. Steps: data preprocessing: prepare the dataset, including handling missing values and feature scaling. Model selection: choose an appropriate machine learning model based on the problem and data. Characteristics: training: train the model using the training data. Prediction: apply the trained model to make predictions on the test data. Metric calculation: compute performance metrics using the predicted and true labels. Metrics: accuracy: the proportion of correctly classified samples. Precision: the proportion of correctly predicted positive samples out of all predicted positive samples. Recall: the proportion of correctly predicted positive samples out of all actual positive samples. F1 score: the harmonic mean of precision and recall. Visualization plots: confusion matrix: a visual representation of the predicted and true labels, showing the number of correct and incorrect predictions for each class. ROC curve: a plot showing the true positive rate against the false positive rate for different classification thresholds, used to assess the model's ability to discriminate between classes. Fine-tune parameters: model hyperparameters adjust the model's internal settings, such as the number of hidden units in a neural network or the regularization strength in a linear model. Data augmentation: generate additional data samples by modifying existing ones to improve the model's robustness and generalization ability. Uncertainty methods: confidence intervals: calculate confidence intervals for the performance metrics to estimate the range of possible values. Bootstrap resampling: repeatedly draw samples with replacement from the dataset to assess the variability of the metrics. Challenges and fixes. Challenge 1: data imbalance. Sample use case that resulted in challenge 1 in a dataset where one class significantly outnumbers the other. The model might always predict the majority class, resulting in high accuracy but poor performance on the minority class. Fixes to challenge 1. Oversampling: duplicate samples from the minority class to balance the class distribution. Undersampling: remove samples from the majority class to reduce the imbalance. Class weighing: assign higher weights to samples from the minority class during training. Challenge 2: model misspecification. Sample use case that resulted in challenge 2: choosing a model that is not suitable for the data, or the task can lead to inaccurate predictions, especially if the data contains complex relationships. Fixes to challenge 2. Try different models: explore a variety of models, including linear, nonlinear, and ensemble methods to find the best fit for the data. Feature engineering: create new features or transform existing ones to improve the model's ability to capture the underlying patterns in the data. Regularization: penalize model complexity during training to prevent overfitting and improve generalization. Challenge 3: data noise. Sample use case that resulted in challenge 3: noise or errors in the data can lead to unpredictable behavior and inaccurate predictions. Fixes to challenge 3: data cleaning: identify and remove outliers or incorrect entries from the data. Robust methods: use robust estimation techniques that are less sensitive to noise and outliers. Feature selection: select the most relevant features that contribute to the target variable, reducing the impact of noisy features.